All right, today we are going to continue our discussion on mathematical induction. Um, oh, whoops. All right, this is what you wrote down yesterday. Let's review it. Okay, you are going to get a statement. Okay, it is going to be the summation of a sequence equals something. Okay, so now the sum of a sequence equals some shortcut. That is your statement that you're getting. All right, your steps. Number one, prove it is true for 1. All right, we have to set up our first domino. Your second step is to show that p sub k makes p sub k plus 1 true. If you can show both of those, then our statement's going to be true for all positive integers. Okay? So first of all, positive integers, all right, we're starting with 1, all right, so we can't have any negatives, all right? And since we're working with a sequence, we're only plugging in integer values, okay? So when we go through these proofs, we are proving these formulas true for positive integers, all positive integers, okay? We have to set up our first domino. If we can show that one domino knocks over the next one, then our whole line of dominoes is going to fall over. Okay? What does that mean as far as what you need to do? It means this. Okay? First of all, you need to show that our formula is true for n is 1. So you're going to have the sum of a sequence. You're going to take your first term. Does that equal when you plug 1 in for the other side of the equation? Okay, that's going to be your easiest step, showing that it's true for 1. It should be true for 1. And realistically, it should be true for when n is 2, when n is 3, when n is 4, but we can't sit here and plug in number after number after number. Okay, we need to show in general that it's going to be true for all positive integers. Okay, so we start with 1. Then we are going to assume. You are literally going to write the word assume in your proof. Assume the formula is true when you have k instead of n. So you're going to write the word assume, and then you're going to write your formula, but instead of n's, you're going to use k's. K is representing a specific integer without actually giving it a value, okay? Then we're going to show that the formula is true for k plus 1, okay? So we are going to have a sum of k terms, and we're going to know what that equals. So we are going to look at the sum, that's this s, okay? The sum of the k plus 1 terms is going to be the sum of the first k terms, and then we're going to add the k plus 1 term, right? If I have the sum of the first 4 terms, then the sum of my first 5 terms is just that plus the 5th term, okay? Same concept. All right, and what we're going to have to do is we're going to have to use algebra to manipulate whatever we have right here to make it look like we need it to for our formula. Okay, this will all make a lot more sense as we go through the proof. Now, once we have shown these 2 steps, I need you to actually summarize what you just did. All right, you need to write a little conclusion. Okay, if you can show these 2 things, then we know our formula is true for all positive integers. So we're actually going to have to conclude our proof. All right, so So you're not going to actually have to write a lot of words. It's going to be a lot of algebra that we're going to do. But you need to make sure you follow step by step how we go through these proofs so that you're going in the logical way for your proof to make sense. Okay? So are there any questions on these two steps? You ready? Here is our first formula that we're trying to prove. Okay, this is saying the sum of the sequence 2n minus 1 equals n squared. The sum of the sequence 2n minus 1 equals n squared. All right? So, our first step is to what? We need to verify n equals 1. All right? So, what is our first term? 1. Is that equal to when I plug 1 in over here? Yes. That's your first step. Okay? Now, technically, when I add the first two terms, 1 plus 3, I should get 2 squared. When I add the first 3 terms, I should get 3 squared. All right? That is what this proof is going to show. All right? Now, second step. What do? We assume, and we write the word assume that S of k is true. So 1 plus 3 plus 5 plus 7 all the way up until 2k minus 1. That should equal, that equals k squared. All I did is I replaced n's with k's. Yes, you have to do this. Okay. We are talking about a specific domino in our little analogy. Okay. All right. Then we will look at the sum of our k plus 1 terms. Okay. So this S of k, that's representing the sum of the first k terms. Right? Now we want to look at the sum of the first k plus 1 terms. Okay? Well, all that is we're going to add up our first k terms, right? And then we're going to tack on the next term, the k plus 1 term. Okay? So since this is the sequence that we're adding up, all right, I'm going to plug k plus 1 in to get my next term. So I summed up my first k terms, and then I added the k plus 1 term. Okay. Now, this is what we're going to work with, and we want to show that this formula is going to work. Okay? So we want to show that this equals what happens when I plug k plus 1 in for the right side of my formula. It is k plus 1 squared. That is what our goal is going to be. We need to show that this formula is the same thing as k plus 1 squared. Okay. Here I have the sum of the first k terms is k squared. So now we're going to work with the first k plus 1 terms, and we need it to equal k plus 1 squared. Okay? Is everyone okay with that? All right. So I'm going to go ahead and rewrite this right here so it looks a little nicer. This is 1 plus 3 plus 5 plus 7. All the way up, this is my k term. plus my k plus 1. Alright, now I'm going to underline something here. What does that represent? Or do you see that somewhere else on our page? That is the same as this right here, right? And what do we know about it? It equals k squared. So we can go ahead and replace that as k squared. Okay. Now our goal is to get to k plus 1, the quantity squared. How might we get from here to here? Factor. K squared plus 2k plus 1. Does that factor to k plus 1 times k plus 1?
Yes.
All right. So with a little bit of manipulation, we have taken our k plus 1 sum. We have shown that it equals k plus 1 squared. Right? So now we're done. So let's conclude. What did we just show? We just showed that 1 plus 3 plus 5 plus 7 all the way to 2n minus 1 equals n squared for all positive integers. I'm going to write it's true for all positive integers. Okay? Therefore, our formula is true for all positive integers. Okay. So let's just recap here. We showed 1 to be true. Our first term equals whatever we plug 1 in over here. We assumed our sum of the k terms is k squared. So then we looked at the sum of the first k plus 1 terms. All right. Now we know what we want it to equal, right? We know we want it to equal k plus 1 squared, which is why we wrote that at the bottom of our page. That's what we're trying to get to.
Did they give you that in the problem? That number on the page?
Well, it's going to be whatever was over here that it equals, right? We're going to plug k plus 1 into that, and that is where we need to get to. Okay? And then in between, we just did some substitution and some algebra until we got to where we needed to be. Questions?
What they're saying from k squared gets there. That's what's wrong.
Which k squared? This one right here? Okay. Well, do you see how I have this green underline? All right. Well, we assumed up here that 1 plus 3 plus 5 plus 7 all the way until 2k minus 1 equals k squared. So we just replaced it. Okay? And that's the point of doing this, is so we can replace that. Okay? That will happen every time.
Yeah, 2k plus 1.
Okay. So here I'm looking at the sum of the k plus 1 terms. So we added our first k term, and then this right here is our next term, our k plus 1 term. So I put k plus 1 into our sequence. Okay? Any other questions? They're great. Will it help to do another one? Couldn't hurt, right?
so confused as to how you know what your bottom answer is supposed to be.
Okay, so back to here.
Yeah.
We want our formula to be true for k plus 1.
Mm-hmm.
So we want it to equal whatever we get when we plug k plus 1 in to this side, to the shortcut side.
Okay.
All right, so here's our next one. First step is to do what? Verify the formula is true for 1. So what is our first sum? Or first term, really? It's 5, because there's only one term. There's really not a sum. All right? Does that equal 1 times 1 plus 4? Yes. All right. Next, we assume. You have to write the word assume. Okay? We're assuming our formula true for k. So we assume 5 plus 7 plus 9 all the way until 3 plus 2k equals k times k plus 4.
Wait, where is the k plus 4? Or k times k plus 4?
All I did is I took s sub n and I replaced all my n's with k's. So,
So I just leave it as
no.
Why do you have to change
was.
N represents all of our positive integers. K is representing a specific integer. Okay?
So wait, why is it 5 equals 1 times 1 plus 4?
Because 5 is our first sum, which is just a term. Okay? And then we plug 1 in over here. Now, we want to look at the sum of our k plus 1 terms. Okay? So the sum of the first k plus 1 terms needs to be the sum of our first k terms, and then we are going to add the next term. So 3 plus 2k is our k term. Now we need to add our k plus 1 term. Okay. Our goal is to get this to equal what? We want our sum to equal k plus 1 times k plus 5. This is why you did your homework yesterday. All right? Our sum of the first k terms is k times k plus 4. So if we're adding up the k plus 1 terms, we want it to be k plus 1 times k plus 5. Okay, all we did is we took what the sum should be for k, and we replaced k plus 1 for k. Alright, so now let's manipulate this to where we can get it to look like k plus 1 times k plus 5. Okay. What is 5 plus 7 plus 9 plus all the way to 3 plus 2k? Okay, we know that from our second step. All right, and then we're adding on the term. What does this become? 5 plus 2k. Okay. All it is now is algebra. Okay. We need to get from this all the way down to k plus 1 times k plus 5. So what should we do? Okay, here we have k squared plus 4k if we distribute, right? Plus 5 plus 2k, which is the same thing as k squared plus 6k plus 5. Now here's what's nice, especially if you don't like factoring, right? We already know what this should factor to, does it? It does. I don't care if you factor it to check or if you work backwards to check, but going from here to here, they factor to k plus 1 times k plus 5. Okay, so we've reached our final destination. We have completed our 2 steps. Therefore, our formula, if you just want to write S sub n, that is fine. Or you can write it out, is true for all positive integers. Yes.
Where do you get all the factoring and stuff? How did you come up with k plus 1?
Yeah, that's right.
Okay. K plus 1 times k plus 5. Where are we getting that? If we go back up to our sum for the first k terms, up here in black. The sum of the first k terms equals k times k plus 4. So the sum of our k plus 1 terms should be whatever this is when we plug in k plus 1. So k becomes k plus 1, k plus 4 becomes k plus 5. I would always write this, once you have the sum of your k plus 1 terms written, I would write what I have right here in green a few lines down so you know what you're actually working towards with your algebra. Okay?
Is it that
No, it will always work out. So if you can't get it to work out or you don't understand how to do your algebra to get there, then you may have messed up somewhere. Okay, because it should always work out. Alright? You have 4 problems. Okay, which isn't a lot, but these take a little bit longer than your 4 problems last night, correct? Okay, I need you to use this work time wisely. I am here to help you, okay? So, please work diligently, that way you can ask me questions if you have them. I am not